Welcome, and thank you for settling in with us tonight. Find a comfortable position, allow your body to sink gently into wherever you are resting, and let your breathing slow to its own natural, unhurried rhythm. Tonight, we are going to take a long and peaceful journey through one of the universe's most quietly extraordinary mysteries, black holes. Drifting softly from the very first moment they were imagined by human minds, through the elegant mathematics that predicted them, and onward into the magnificent, still darkness where they silently reside. These are not stories of violence or destruction. These are stories of order, of the universe folding gently inward, of space-time curving with quiet dignity, of light that travels so far and so faithfully, only to find its final resting place in the deepest, most serene corners of the cosmos. There is nothing you need to do, nowhere you need to be. Simply rest, breathe, and allow the quiet wonders of the universe to carry you softly towards sleep. Let each fact wash gently over you like a slow, warm tide, carrying you a little further from the noise of the day, and a little closer to that calm, unhurried place where the mind finally grows still. 100 soft and wondrous facts lie ahead of you tonight, each one a quiet step deeper into the universe's most extraordinary secret. There is no hurry. There is no rush. Only the gentle turning of the cosmos and the soft, patient voice of science, offering everything it knows about the beautiful darkness between the stars. So whenever you are ready, let us begin. A black hole is not, as many people imagine, an empty void swirling in space. It is, in fact, an extraordinarily dense concentration of mass so tightly packed that the gravitational pull it generates becomes completely inescapable beyond a certain boundary, known as the event horizon. Imagine taking the entire mass of our Sun, all of that burning, churning golden energy, and compressing it down into a sphere no wider than a few miles across, and you will begin to approach the quiet, astonishing density that gives a black hole its nature. The region inside a black hole is not a tunnel or a hole in any conventional sense. It is more like a region of space where the rules of the universe become deeply, peacefully different from anything we experience here on Earth. Scientists describe black holes not as destructive forces, but as some of the most perfectly organized and mathematically elegant structures that the universe has ever produced. The phrase black hole was introduced into scientific language by the American physicist John Archibald Wheeler during a lecture he gave in 1967, and the term caught on with remarkable speed because it so perfectly captured the quiet, dark elegance of what these objects truly are. Before Wheeler's naming, scientists referred to these regions using far more technical and less evocative language, calling them gravitationally collapsed objects or frozen stars, descriptions that were accurate but failed to convey the poetic depth of what they represented. Wheeler was known throughout his career for his ability to find language that made physics feel alive and approachable, and with two simple words, he gave the universe one of its most enduring and recognizable concepts. The story of how a single scientist, standing at a podium in New York, gave a name to one of the cosmos's deepest secrets is, in its own quiet way, one of the most beautiful moments in the long history of human curiosity. In 1915, Albert Einstein published his general theory of relativity, a framework so revolutionary that it rewrote humanity's understanding of gravity, space, and time, and embedded within those beautiful equations was the quiet mathematical possibility of black holes, though Einstein himself was not entirely certain such things could truly exist in nature. The equations of general relativity described how mass curves the fabric of space-time the way a heavy object placed on a stretched rubber sheet creates a dip, and when the math was pushed to its extremes, it revealed that a sufficiently massive object would curve space-time so severely that nothing could escape. Einstein spent much of his later years uncertain about whether these extreme solutions to his own equations were physically real or merely mathematical curiosities, and there is a gentle irony in the fact that his formulas described black holes decades before any human instrument could detect one. The relationship between Einstein's quiet, thoughtful work in a patent office and the universe's grandest objects is one of the most quietly stunning connections in all of science. Just weeks after Einstein published his general theory of relativity in 1915, the German physicist and astronomer Karl Schwarzschild, while serving on the Eastern Front during the First World War, managed to find the first exact solution to Einstein's field equations. A solution that described the geometry of space-time around a perfectly spherical mass. This solution, known today as the Schwarzschild metric, laid the mathematical foundation for everything we understand about black holes. And it is remarkable to consider that such a profound scientific achievement was accomplished by a man sitting in the cold of a military encampment, working through equations by firelight. Schwarzschild sent his solution to Einstein in a letter, and Einstein replied with admiration, genuinely moved that such elegant mathematics had emerged from such difficult circumstances. Schwarzschild passed away just months later from an illness contracted at the front, leaving behind a mathematical legacy that would quietly reshape humanity's view of the cosmos for the next century. Every object in the universe, from a grain of sand to the largest star, has what is known as a Schwarzschild radius, the theoretical size to which it would need to be compressed in order to become a black hole, and for our own Earth. That radius is approximately the size of a small marble, about 9 millimeters across. For our Sun, the Schwarzschild radius is roughly 3 kilometers, meaning that if all of the Sun's mass were somehow gathered into a sphere just 3 kilometers wide, the curvature of space-time around it would become so extreme that even light itself could not pull away from its gravitational grip. These numbers are not just scientific curiosities. They are a quiet reminder that the universe does not reserve its most extraordinary possibilities for the distant and the exotic. The mathematics of black holes applies to every piece of matter in existence. There is something deeply meditative about sitting with the idea that this ordinary world around you, these familiar objects and landscapes, carry within them the same mathematics that governs the universe's most ancient and spectacular formations. Scientists currently recognize four main categories of black holes, each distinguished by its mass and the way it came into being, and together they form a family of cosmic structures that spans an extraordinary range of scales from stellar to almost unimaginably vast. The first and most commonly formed type is the stellar black hole, which is born from the gravitational collapse of a very massive star at the end of its long, luminous life, and these typically have masses between roughly 3 and several tens of times the mass of our Sun. The second type is the intermediate black hole, which sits in the middle of the mass range and remains one of the least understood members of the family, with masses ranging from hundreds to hundreds of thousands of solar masses. Then there are the supermassive black holes, which anchor the centers of most large galaxies in the universe, and the hypothetical primordial black holes, thought to have formed in the very early moments of the universe's quiet beginning. At the center of nearly every large galaxy in the observable universe, including our own Milky Way, astronomers have found evidence of a supermassive black hole. An object so massive that it contains millions or even billions of times the mass of our Sun, sitting quietly at the galactic core like the still eye of an endlessly slow cosmic spiral. The supermassive black hole at the center of the Milky Way is known as Sagittarius A*, and it has a mass of approximately 4 million times that of our Sun, occupying a region of space roughly the size of our solar system, a sobering comparison that reveals just how efficiently these objects pack matter into space. Despite their extraordinary mass, supermassive black holes are not the voracious cosmic consumers of popular imagination. Most of them, including Sagittarius A*, spend the vast majority of their existence in a quiet, dormant state, neither actively consuming large quantities of matter nor producing dramatic visible effects. The idea that at the very center of the beautiful, soft spiral of stars we call home there rests one of the universe's most quietly powerful structures has a certain poetic harmony, a still center around which everything gently turns. The event horizon is one of the most conceptually beautiful boundaries in all of science. It is the invisible spherical surface surrounding a black hole beyond which no information, no light, and no matter can return to the outside universe, not because of a wall or a barrier, but simply because of the geometry of space-time itself. If you were to float gently toward an event horizon in the far future of science fiction and cross it, you would not feel a dramatic physical sensation at that precise moment. The crossing of the event horizon is not an experience of impact but rather the quiet, irreversible conclusion of a journey, the moment after which all paths through space-time lead only inward. The size of the event horizon is directly proportional to the mass of the black hole, meaning that more massive black holes have larger event horizons. And a sufficiently massive black hole's event horizon could be larger than the entire orbit of Pluto around our Sun. Scientists describe the event horizon not as a physical surface but as an informational boundary, a line in the geometry of the universe that separates the knowable from the forever unreachable. One of the most quietly astonishing consequences of general relativity, and one that has been confirmed through observation and experiment, is that time itself does not flow at the same rate everywhere in the universe. Near a source of very strong gravity, such as a black hole, time passes more slowly than it does in regions of weaker gravity. This phenomenon, known as gravitational time dilation, means that an astronaut hovering near the event horizon of a black hole would experience time passing far more slowly than their colleagues left behind in the distant reaches of space. Hours near the black hole might correspond to years or decades back home. The mathematics of this effect are embedded in Einstein's equations and have been tested and confirmed here on Earth, where extremely precise atomic clocks placed at different altitudes, and thus different gravitational strengths, do indeed tick at measurably different rates. There is something deeply serene about this truth, that the universe does not keep a single universal clock, but instead allows time to flow like a river, moving more slowly where gravity runs deep and more swiftly where the pull of mass is gentle. On April 10, 2019, humanity achieved something that had been theorized, debated, and dreamed about for over a century. the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow, capturing the supermassive black hole at the center of a galaxy called Messier 87, which lies approximately 55 million light-years from Earth. The image showed a bright, glowing ring of orange and golden light, the superheated gas of the accretion disk, surrounding a central dark region. The shadow of the black hole itself, and it matched the theoretical predictions of general relativity with extraordinary precision. The Event Horizon Telescope was not a single instrument but a coordinated network of 8 radio observatories positioned across the globe, from Hawaii to Antarctica, that worked together to effectively create a telescope the size of the entire Earth. The team behind the image included over 200 scientists from 20 countries. And among them was a young computer scientist named Katie Booman, whose algorithm played a central role in assembling the blurry data collected by those scattered telescopes into the historic, quietly glowing portrait of the universe's most elusive object. 3 years after the historic image of M87*, the Event Horizon Telescope collaboration achieved another quiet milestone on May 12, 2022. They released the first image of Sagittarius A*, the supermassive black hole at the very center of our own Milky Way galaxy, located approximately 26,000 light-years from Earth. The image was technically far more challenging to produce than the M87* image, because Sagittarius A* is both much closer and much smaller, meaning that the hot gas swirling around it moves so quickly that it changes appearance in the time it takes to gather data. Astronomers described imaging Sagittarius A* as trying to take a clear photograph of a fast-moving puppy, while imaging M87* was more like photographing a slowly strolling dog. The final image revealed the same beautiful ring of glowing light in amber and orange tones, surrounding the soft dark shadow that marks the boundary of one of the most massive objects in our galactic neighborhood. There is a particular intimacy in knowing that this image of our own galaxy's central black hole is, in cosmic terms, a portrait of home. In 1974, the British theoretical physicist Stephen Hawking made a discovery so unexpected and so elegant that it fundamentally changed our understanding of black holes. He showed mathematically that black holes are not entirely black, but instead emit a very faint, very cold glow of thermal radiation now known as Hawking radiation. This radiation arises from the subtle, quantum mechanical behavior of the vacuum of space near the event horizon, where pairs of particles and antiparticles are constantly flickering into brief existence and then annihilating, but occasionally, one partner falls into the black hole while the other escapes, carrying away a tiny amount of energy. The temperature of Hawking radiation is inversely proportional to the mass of the black hole, meaning that smaller black holes glow slightly warmer than larger ones, though even for a black hole the size of a mountain. This glow would be unimaginably cold, far colder than the cosmic microwave background that fills all of space. Hawking radiation has never yet been directly detected, because the black holes we know of are far too massive and therefore far too cold in their radiation. But its mathematical existence is considered one of the most beautiful and important theoretical results in modern physics. At the very heart of a black hole, according to the mathematics of general relativity, lies a singularity. A point of theoretically infinite density where the fabric of spacetime curves without bound, and where the equations of known physics reach their quiet, elegant limit. The singularity is not well understood, and most physicists believe that the concept of a true infinity of density is a signal that our current theories are incomplete. That somewhere between the scale of general relativity and the scale of quantum mechanics, a deeper theory is waiting to be discovered that will smooth out this mathematical roughness and reveal the true nature of what lies at a black hole's center. Some of the most beautiful and speculative ideas in theoretical physics, including loop quantum gravity and string theory, offer different visions of what might replace the singularity, suggesting perhaps a region of maximum but finite density, or a point at which space-time takes on a fundamentally different character. The singularity is physics' most honest admission of its own boundaries. And there is something quietly wonderful about the fact that at the darkest center of the universe's most opaque structures, humanity's understanding reaches out gently toward the unknown. One of the most intriguing physical properties of a black hole is that it can rotate, and many, perhaps most, of the black holes in the universe do rotate, spinning at rates that can approach the theoretical maximum allowed by the laws of physics. A rotating black hole is described by a different set of equations than a non-rotating one. Specifically, the Kerr metric, discovered by New Zealand mathematician Roy Kerr in 1963, and this rotation introduces a remarkable effect called frame dragging, where the spinning black hole literally drags the surrounding fabric of spacetime along with it like a slow whirlpool in a quiet river. The region of spacetime that is dragged into rotation around a spinning black hole is called the ergosphere, a gently oblate region outside the event horizon where the very geometry of space is pulled into motion, and within this region, no object can remain stationary relative to the distant stars, no matter how powerful its engines. Some black holes are observed to spin at rates approaching 98 or 99% of the theoretical maximum, a condition that stretches spacetime into shapes of spectacular mathematical beauty. Among all the black holes that astronomers have identified and measured, the current record holder for sheer size is a black hole known as TON 618. A supermassive black hole located approximately 10.4 billion light-years from Earth, embedded within a highly luminous quasar in the constellation Canes Venatici. TON 618 has a mass of approximately 66 billion times the mass of our Sun, a number so large that it becomes almost more poetic than mathematical. And its event horizon has a radius of roughly 200 billion kilometers, which is about 1,300 times the distance from our Sun to the Earth. To put that in still gentler perspective, the event horizon of TON 618 is so wide that if it were placed at the center of our solar system, it would extend well beyond the orbit of Pluto and engulf the entire planetary family of our Sun. And yet, for all its staggering dimensions, TON 618 sits serenely in the distant universe. A structure of almost serene mathematical simplicity, defined entirely by just three numbers: its mass, its spin, and its electric charge. One of the most elegantly simple and quietly profound facts about black holes is that no matter how much matter, light, or complex information falls into one, the black hole itself is completely described by just three numbers: its mass, its angular momentum, or spin, and its electric charge. This principle, sometimes referred to in physics as the no-hair theorem, suggests that all the rich complexity of the matter that falls into a black hole. Every atom, every molecule, every pattern, is effectively erased, and only these three simple numerical fingerprints remain. The no-hair nickname was coined as a playful reference to the idea that black holes have no distinguishing features beyond these three properties. No hair, no texture, no individuality beyond what those numbers describe. There is a quiet, almost meditative beauty in the thought that the universe's most complex-seeming objects are, at their core, among the most mathematically simple, elegant summaries of everything that went into them. A common and enduring misunderstanding about black holes is that they actively pull in surrounding matter the way a vacuum cleaner pulls in dust. But this is not how gravity works. A black hole's gravity is powerful, but it behaves exactly like the gravity of any other massive object at the same distance. If our Sun were somehow to be replaced by a black hole of the same mass, an event purely of thought and imagination, Earth would not be pulled inward or disturbed in any dramatic way. It would continue to orbit the black hole on exactly the same path it currently follows around the Sun. The difference with a black hole arises only at very close range, where the concentration of mass in such a small space means that the gravitational field becomes extraordinarily steep. But at a safe distance, a black hole is gravitationally no more demanding than a star of the same mass. This is a reassuring and grounding thought, that the universe, even in its most extreme configurations, follows the same patient, universal laws that govern the gentle fall of autumn leaves. Among the most luminous objects in the observable universe are quasars, quasi-stellar objects that blaze with light so intense that they outshine entire galaxies of hundreds of billions of stars. And at the heart of every quasar there is a supermassive black hole, actively consuming material from its surrounding accretion disk. As matter spirals into the black hole along the accretion disk, it is compressed and heated to temperatures of millions of degrees. And a fraction of its mass energy is converted into radiation and emitted outward with breathtaking efficiency, more efficient, in fact, than any nuclear reaction that occurs within a star. Quasars were first identified in the 1950s and 1960s as mysterious radio sources that seemed to be point-like but impossibly bright, and it took years of careful observation and theoretical work before scientists understood that they were looking at the most energetically active black holes in the young universe. The brightest known quasar, J05294351, was identified in 2024 and is estimated to consume matter equivalent to roughly one sun every single day, releasing energy that makes it the most luminous object yet discovered in the known cosmos. One of the most spectacular and visually dramatic features associated with actively feeding black holes is the formation of relativistic jets, narrow, intensely focused beams of plasma and energy that shoot outward from the poles of a black hole's accretion disk at velocities approaching the speed of light. These jets can extend for extraordinary distances, in some cases, thousands or even millions of light-years from the black hole, carving long, glowing channels through the intergalactic medium and depositing enormous amounts of energy into the universe around them. The exact mechanism by which these jets are formed is still an active area of research. But most models involve the powerful magnetic fields generated by the rotating accretion disk, which act to focus and accelerate material into these tight, brilliant streams. The Centaurus A galaxy, located about 13 million light-years from Earth, has a particularly beautiful and well-studied pair of jets emerging from its central supermassive black hole. And radio telescope images of Centaurus A reveal these jets as softly glowing plumes extending across a remarkable portion of the sky. Current cosmological estimates suggest that the observable universe contains somewhere in the range of 40 quintillion stellar mass black holes. That is, 40 followed by 18 zeros, a number so vast that it begins to dissolve into something that feels more like poetry than arithmetic. These black holes are the remnants of massive stars that lived their long, slow lives and then collapsed inward at the end of their stellar journeys. And they are distributed throughout every galaxy in the observable universe, many of them wandering in quiet darkness far from any source of matter to illuminate them. For comparison, the Milky Way galaxy alone is estimated to contain somewhere between 10 million and 1 billion stellar black holes. Most of them completely invisible against the dark background of space, detectable only when they happen to interact with a companion star or pass in front of a distant light source. There is a gentle and meditative quality to the image of a universe quietly filled with so many dark, patient, perfectly described objects, resting in the stillness of space, undisturbed, awaiting the slow unfolding of cosmic time. Near a black hole, the difference in gravitational pull between the near side and the far side of any object creates what physicists call tidal forces. The same family of forces, though far gentler in everyday experience, that cause Earth's oceans to bulge outward toward the moon and create the rhythm of the tides. For a stellar mass black hole, these tidal forces near the event horizon would be extraordinarily intense. But for a sufficiently large supermassive black hole, one with a mass of billions of solar masses, the tidal forces at the event horizon are actually quite gentle, because the event horizon is so far from the central singularity. This means that an object crossing the event horizon of a truly massive black hole would not immediately experience any dramatic physical sensation. The horizon itself would simply be an invisible geometric boundary crossed without fanfare. The process by which tidal forces from a black hole stretch an object is given the wonderfully descriptive technical name spaghettification. A term that carries, in its own gentle and almost whimsical way, a vivid and accurate picture of what the physics describes. One of the deepest and most beautifully unresolved questions in theoretical physics is known as the black hole information paradox. A puzzle that arises from the apparent conflict between two of physics' most successful and cherished theories, general relativity and quantum mechanics. Quantum mechanics holds that information about the state of a physical system can never be truly destroyed. It may be scrambled or transformed. But the total information content of the universe is conserved, like a perfect cosmic accounting system that never loses a single entry. But if Hawking radiation causes black holes to slowly lose mass and eventually cease to exist, what happens to all the information encoded in the matter that fell into the black hole over its lifetime? Does it disappear forever, violating quantum mechanics, or is it somehow encoded in the outgoing radiation in a form we do not yet understand? Stephen Hawking spent much of his career wrestling with this paradox and eventually came to believe that information was indeed preserved. though the mechanism of its preservation remains one of the most active and exciting open questions in physics today. Surrounding a black hole at a specific distance just outside the event horizon is a region known as the photon sphere. A thin shell in spacetime where the gravitational pull is so precisely balanced with the trajectory of light that photons can travel in circular orbits around the black hole, looping endlessly in perfectly curved paths. For a non-rotating black hole, the photon sphere sits at a distance of exactly 1.5 times the Schwarzschild radius, and if you could somehow position yourself at this distance and aim a flashlight directly sideways, the beam of light would curve all the way around the black hole and eventually return to illuminate the back of your head. The photon sphere is not a physical surface but rather a mathematical region, and it is unstable. Any photon that is nudged even slightly inward will spiral into the black hole, while any photon nudged slightly outward will slowly escape to infinity. The dark shadow that appears at the center of black hole images, like the ones captured by the Event Horizon Telescope, is related to this photon sphere, as it represents the region of space from which no photons can escape to reach our telescopes. When two black holes orbit each other in a binary system, they do not remain in stable orbit forever. Instead, general relativity predicts that they will slowly, over vast stretches of cosmic time, lose energy by radiating gravitational waves and gradually spiral inward toward each other until they finally merge into a single, larger black hole. This merger is not an explosive event in the conventional sense, but rather a gradual geometric reshaping of spacetime, the two event horizons approaching each other, distorting and elongating before finally connecting and settling into the smooth, quiet geometry of a single rotating black hole. The moment of merger sends ripples through the fabric of spacetime, gravitational waves that propagate outward across the universe at the speed of light, carrying with them a precise record of the masses and spins of the merging black holes encoded in the pattern of the waves. On September 14, 2015, the LIGO Observatory made history by detecting for the first time the gravitational waves from just such a merger. Two black holes with masses of about 29 and 36 solar masses that had spiraled together approximately 1.3 billion light-years from Earth. Gravitational waves are not sound waves or light waves or any kind of disturbance in a medium. They are literal oscillations in the geometry of spacetime itself, stretching and compressing the distance between objects in perpendicular directions as they pass through, and doing so with a gentleness that makes them extraordinarily difficult to detect. The LIGO detectors that first observed gravitational waves are L-shaped interferometers with arms 4 kilometers long, and the signal from the first detected merger stretched and compressed those arms by a distance of about 1/1000th the diameter of a proton. A measurement so precise it represents one of the most technically demanding scientific achievements in human history. Albert Einstein himself predicted the existence of gravitational waves in 1916, just a year after publishing General Relativity. But he doubted they would ever be measurable, believing the distortions they caused were simply too small for any conceivable instrument to detect. The detection of gravitational waves in 2015, nearly a century after Einstein's prediction, by an observatory he could scarcely have imagined, was quietly confirmed as one of the greatest moments in the history of physics, earning the LIGO team the Nobel Prize in Physics in 2017. Over the past few decades, astronomers at observatories in Hawaii and Chile have patiently tracked the motions of individual stars in the dense star cluster near the center of the Milky Way. And the paths those stars trace through space have revealed the invisible presence of Sagittarius A** with remarkable precision. Stars near the galactic center, designated with names like S2 and S62, move in elliptical orbits at extraordinary speeds, S2. For instance, reaches velocities of about 7,650 kilometers per second at its closest approach to Sagittarius A*, which is roughly 2.5% of the speed of light. By tracking these stellar orbits for years and years with the patience of dedicated scientists who devoted their careers to watching a single region of sky, researchers were able to determine that the mass at the center of those orbits, invisible, dark, and compact, is approximately 4 million solar masses, consistent only with a black hole. This painstaking work earned Andrea Ghez-Uckler and Reinhold Genzel of the Max Planck Institute a share of the 2020 Nobel Prize in Physics. A recognition that rewarded not dramatic experiments but decades of quiet, careful watching of the sky. A consequence of Hawking's theoretical work on black hole radiation is that black holes can be assigned a temperature, specifically the temperature of the Hawking radiation they emit, and this temperature is inversely related to the black hole's mass. For the supermassive black hole Sagittarius A*, with its mass of 4 million suns, the Hawking temperature is estimated to be approximately 0.0000000000000015 Kelvin. A number so close to absolute zero that it is far colder than even the cosmic microwave background radiation that permeates all of space at about 2.7 Kelvin. This means that supermassive black holes are, in a very real thermodynamic sense, the coldest known objects in the universe. Colder than the darkest vacuum of intergalactic space, colder than the most advanced refrigeration systems built by human hands. There is a quiet and unexpected poetry in the fact that the most gravitationally intense objects in the cosmos are also, thermodynamically speaking, among the most tranquil and cold. Black holes do not hover motionlessly in space. They are carried along with the stars and gas clouds around them, moving through the galaxy at velocities that can range from relatively modest to extraordinarily fast, depending on how they were formed and what gravitational interactions they have experienced. Some black holes are set into rapid motion at the moment of their formation, if the collapsing star that created them is not perfectly symmetric and ejects mass unevenly during the process. This asymmetry gives the newborn black hole a gravitational kick that sends it moving through the galaxy at high velocity. Astronomers have identified runaway black holes traveling at speeds of several hundred kilometers per second relative to the surrounding stars, moving through the galaxy at a pace that, while fast by any everyday standard, represents the quiet and steady drift of a cosmic wanderer. In 2023, astronomers reported the possible discovery of a stellar-mass black hole moving so fast through the Milky Way that it appeared to have left a trail of compressed gas and young stars in its wake, a trail of creation rather than destruction, a quiet sculptor passing through the galaxy. The largest structures in the universe, the vast network of galaxy filaments, sheets, and voids known as the cosmic web, have been shaped over billions of years in part by the activity of supermassive black holes at the centers of galaxies, which regulate the growth of their host galaxies by heating and stirring the surrounding gas. When a supermassive black hole enters an active phase and begins consuming large quantities of material, it releases enormous amounts of energy in the form of radiation and jets that heat the surrounding gas in the galaxy and the broader intergalactic medium, slowing or halting the formation of new stars. This process, known as AGN, active galactic nucleus feedback, is believed to be one of the key mechanisms that prevents galaxies from growing without limit, giving them the characteristic sizes and structures we observe today. The cosmic web that we see in detailed simulations of the universe, those beautiful, filamentary structures that look like glowing threads connecting bright nodes of galaxy clusters, bears the imprint of billions of years of black hole activity woven into its geometry. Stellar mass black holes, the most numerous type in the universe, are born from the collapse of extremely massive stars, typically those with masses greater than about 20 to 25 times that of our Sun, when those stars reach the end of their long hydrogen-burning lives and can no longer support themselves against the inward pull of gravity. As the star's core collapses under its own weight in a matter of seconds, the outer layers may be ejected in a supernova explosion, while the core itself compresses beyond the neutron star threshold into the incomparable density of a black hole, a transformation from a vast, luminous sphere of burning gas into a compact, dark, silent object in less time than it takes to draw a breath. Not all massive star collapses produce a visible supernova. Some stars may collapse almost silently, their outer layers falling directly into the forming black hole in what astronomers call a failed supernova, a quiet disappearance rather than a brilliant finale. The Milky Way galaxy contains hundreds of millions of these stellar corpses, patient, dark travelers distributed throughout our galactic home, most of them forever invisible to any instrument we currently possess. Between the stellar mass black holes born from collapsing stars and the supermassive giants at galactic centers, there exists a tantalizing category known as intermediate mass black holes. Objects with masses ranging from roughly 100 to 100,000 solar masses, which represent one of the most actively sought and least fully understood members of the black hole family. For many years, observational evidence for intermediate mass black holes was sparse and debated, and some astronomers wondered whether they truly existed as a distinct population or whether the universe simply jumped from stellar mass to supermassive without passing through an intermediate stage. In recent years, however, evidence has been accumulating from gravitational wave detections, observations of dense star clusters, and ultracompact X-ray sources that intermediate mass black holes do indeed exist, perhaps forming through the repeated mergers of smaller black holes or the direct collapse of very massive early stars. The question of how supermassive black holes grew to their current enormous sizes in the early universe, within just 1 billion years of the Big Bang, is intimately connected to whether intermediate black holes served as the seeds from which those giants grew. Before a stellar remnant becomes a black hole, it may pass through a stage as a neutron star, one of the most exotic and densely packed objects in the universe, composed almost entirely of neutrons packed together so tightly that a teaspoon of neutron star material would weigh approximately 1 billion tons here on Earth. But neutron stars have a mass limit above which even the pressure of tightly packed neutrons cannot resist the inward pull of gravity. This limit is known as the Tolman-Oppenheimer-Volkoff limit, and it lies somewhere in the range of about 2 to 3 solar masses. Above this limit, no known force in nature can halt the gravitational collapse, and the neutron star continues to compress inward, crossing the threshold of neutron star density and continuing into the perfect, quiet compression of a black hole. The exact value of the Tolman-Oppenheimer Volkoff limit is still not precisely known, because it depends on the equation of state of neutron-dense matter, a detail of nuclear physics that remains one of the active frontiers of astrophysical research. Many of the stellar mass black holes we have actually detected and measured are found in X-ray binary systems, pairs in which a black hole orbits closely with a companion star, slowly drawing gas from the star's outer atmosphere into an accretion disk that glows brilliantly in X-rays as the infalling material is heated to millions of degrees. The first stellar mass black hole candidate ever confirmed, Cygnus X1, located about 6,000 light-years from Earth in the constellation Cygnus, was identified as an X-ray binary in the early 1970s through observations that revealed a compact, massive invisible object drawing material from a large blue supergiant companion star. Cygnus X1 has a mass of about 21 solar masses, rotates at more than 800 times per second, and is one of the brightest X-ray sources visible in the sky, a softly violent but quietly beautiful system in which a star slowly gives its outer layers to a patient, dark companion. X-ray binary systems have provided some of the most direct and reliable measurements of black hole masses, spins, and behaviors, and they continue to be important observational laboratories for testing the physics of extreme gravity. One of the most visually striking consequences of a black hole's gravitational influence on the surrounding spacetime is the phenomenon of gravitational lensing, the bending of light rays from distant objects as they pass close to the black hole, causing those distant objects to appear distorted, multiplied, or amplified. When a black hole passes precisely between Earth and a distant star or galaxy, the gravitational lensing can produce a beautiful circular image known as an Einstein ring, a perfect, glowing loop of light representing the distorted image of the background object smeared symmetrically around the lens. In cases where the alignment is not perfect, the background object may appear as two or more separate images, arcs, or even dramatically brightened point sources, and by analyzing the pattern of lensing, astronomers can measure the mass of the lensing object even if it is completely invisible in ordinary light. Gravitational lensing has been used to discover black holes wandering alone through the Milky Way, detected as brief, characteristic brightenings of background stars, a technique called microlensing that uses the geometry of light to reveal the presence of darkness. The study of black holes has contributed deeply to physicists thinking about one of the most philosophically rich questions in all of science. Why does time flow in a particular direction, forward and never backward, even though most of the fundamental equations of physics look exactly the same whether time runs forward or in reverse? The thermodynamics of black holes, including the idea that a black hole's entropy is related to the area of its event horizon and can only increase, provides one of the most beautiful and far-reaching connections between the behavior of black holes and the second law of thermodynamics, which underlies the arrow of time. Jacob Bekenstein, a physicist who worked with Wheeler and later Hawking, made the remarkable theoretical step of assigning entropy to a black hole in proportion to its event horizon area, an idea that at first seemed strange and even incorrect to many physicists, but which turned out to be one of the most profound insights in modern theoretical physics. The connection between black holes, entropy, information, and the direction of time remains one of the deepest threads connecting the physics of the very large with the physics of the very small, and unraveling it may be one of the great intellectual achievements waiting in humanity's future. Building on Bekenstein's work connecting black holes and entropy, theoretical physicists discovered something deeply unexpected. The entropy of a black hole is proportional not to its volume, as one might intuitively expect, but to the area of its event horizon, a two-dimensional surface. This finding led to the development of what is now called the holographic principle, the remarkable and deeply counterintuitive idea that all the information needed to describe the physics of a region of space might be encoded on the boundary of that region, just as a two-dimensional hologram contains three-dimensional information. The holographic principle was given a powerful and precise formulation by physicist Juan Maldacena in 1997, in a theoretical framework known as the ADS-CFT correspondence, which relates a theory of gravity in a particular kind of curved space to a quantum field theory on its boundary, without any gravity at all. Though these ideas remain theoretical and mathematical, they have become some of the most discussed and deeply investigated concepts in modern fundamental physics, suggesting that the universe itself might be, in some deep sense, a hologram, a universe of three dimensions written in the language of two. Among the most intriguing and as yet unconfirmed members of the black hole family are primordial black holes, hypothetical objects thought to have formed not from the collapse of stars, but directly from the extreme density fluctuations of matter in the first fractions of a second after the Big Bang, before any stars had yet formed. If density fluctuations in the very early universe were sufficiently large in certain regions, those regions could have collapsed directly into black holes whose masses are entirely unrelated to any stellar formation process, potentially ranging from microscopic to thousands of solar masses. Primordial black holes, if they exist, are of enormous scientific interest because they could account for some or all of the universe's mysterious dark matter, the invisible substance whose gravitational effects are observed throughout the cosmos but whose nature remains completely unknown. No primordial black hole has yet been definitively confirmed, and the question of whether they exist, and in what abundance, is one of the most actively debated frontier questions connecting cosmology, particle physics, and the observational study of black holes. Dark matter, the invisible form of matter that is inferred from its gravitational effects on galaxies and large-scale structure, and which makes up roughly 27% of the total energy content of the universe, has long been one of the deepest mysteries in cosmology, and black holes have been proposed as one possible explanation for at least some of its gravitational influence. Primordial black holes, in particular, have been suggested as dark matter candidates, and observational campaigns using gravitational microlensing, watching for the brief brightening of background stars when a massive unseen object passes in front of them, have been used to constrain how many primordial black holes could exist in various mass ranges. Current observations suggest that primordial black holes cannot account for all of the dark matter if they fall in certain mass ranges, but windows remain open for black holes in the mass range of a few tenths of a solar mass or less, and the question is still being actively investigated. The intersection of the black hole question and the dark matter question is one of the most fertile grounds in contemporary astrophysics, where two profound mysteries touch each other gently and may, in the end, illuminate both. Because Hawking radiation causes black holes to slowly lose mass over time, a black hole has a finite lifetime, though for the black holes we observe in the universe today, that lifetime is almost incomprehensibly long, stretching far beyond the current age of the universe. A black hole with the mass of our Sun would have a Hawking evaporation lifetime of approximately 2 times 10 years. That is 2 followed by 67 zeros, a span of time so vast compared to the current age of the universe, approximately 13.8 billion years, that it dissolves into something more like a concept than a quantity. The supermassive black hole at the center of M87, with its mass of 6.5 billion solar masses, would have a Hawking lifetime on the order of 10 to the power of 1 years, a number that cannot be meaningfully visualized in any familiar terms, only appreciated as a symbol of the universe's extraordinary patience. In the deepest, quietest future of the cosmos, a future where all the stars have long since burned out and the galaxies have dissolved, black holes will still be gently glowing with their infinitesimally faint Hawking radiation, the last luminous objects in an otherwise dark and cooling universe. One of the deep reasons that nothing can escape a black hole once inside the event horizon is that in Einstein's theory of relativity, the speed of light is the absolute upper limit of how fast any object or signal can travel, and inside the event horizon, all paths through space-time, even those directed outward, lead only toward the singularity. This is not a limitation of technology or engineering but a geometric reality of space-time itself. Inside the event horizon, the direction of increasing time and the direction toward the singularity are the same direction, and escaping would require traveling faster than light, which the geometry of relativity does not permit. The speed of light, approximately 299,792 kilometers per second in a vacuum, sets the pace of the entire universe, governing not just the speed of photons but the speed of gravity, the speed of all causal influence, and the fundamental rate at which information can propagate from one place to another. This cosmic speed limit is what makes the event horizon a true point of no return, not a wall, not a force, but a quiet geometric boundary beyond which the landscape of space-time itself channels all futures inward. In addition to mass and spin, black holes can in principle carry electric charge. This is the third and final property that the no-hair theorem permits black holes to possess, and it gives rise to a class of theoretical black hole solutions known as Reissner-Nordström black holes for charged non-rotating ones, or Kerr-Newman black holes for those that are both charged and spinning. A charged black hole would produce both a gravitational field and an electric field in its exterior spacetime, and its structure would differ subtly from an uncharged one, possessing, for instance, two event horizons rather than one for certain combinations of charge and mass. In practice, astrophysicists believe that real black holes in the universe carry little or no net electric charge, because the universe is electrically neutral on large scales and any charge carried by a black hole would quickly be neutralized by attracting particles of the opposite charge from the surrounding medium. Nevertheless, the mathematically complete family of black hole solutions, with all combinations of mass, spin, and charge, represents one of the most elegant structures in all of theoretical physics, a complete classification of possible black hole types that took decades of mathematical work to assemble. When the LIGO detector recorded the first gravitational wave signal from a black hole merger in September 2015, scientists were able to convert the pattern of that signal, the rising and falling frequency and amplitude of the gravitational wave, into an audio signal that humans could hear, and the result was a brief, gentle chirp. The chirp lasted for about 1/5 of a second at the end of the signal, as the two black holes spiraled together and merged, and it sounded something like a soft, rising tone, similar to the brief musical note that might come from a gentle pluck of a string, low and quiet and barely there. This chirp, produced by the merger of two black holes over 1 billion light-years away, was the first sound ever heard from the universe that did not travel to us as electromagnetic radiation, the first message received through the new sense of gravitational wave astronomy. Listening to it for the first time, many of the scientists in the LIGO collaboration reported a feeling of profound quietness, a sense of having heard something ancient and enormous communicated in the most delicate and understated of whispers. The process of stars evolving, collapsing, and in some cases forming black holes has played a central role in creating the chemical elements that make up everything we see around us, including the atoms in our bodies, the soil beneath our feet, and the air in our lungs. Massive stars that eventually collapse to form black holes are among the most productive cosmic forgers of heavy elements, producing through nuclear fusion processes elements from carbon and oxygen all the way through to iron, nickel, and beyond through explosive processes at the end of their lives. The merger of neutron stars, compact objects that are the immediate predecessors of some black holes, has been confirmed to produce gold, platinum, and other heavy elements in enormous quantities through a process called rapid neutron capture, or the R process. The black hole that forms after such a merger inherits the gravitational legacy of these ancient, element-forging processes, meaning that somewhere in the history of every black hole is a story of stellar nucleosynthesis, a tale of atoms being built from smaller pieces in the quiet interior of a massive star. In 1969, the British mathematical physicist Roger Penrose, who would later share the 2020 Nobel Prize in Physics for his work on black holes, discovered that it is theoretically possible to extract rotational energy from a spinning black hole, a process now known as the Penrose process. The Penrose process works within the ergosphere, the region just outside the event horizon of a spinning black hole where spacetime is dragged into rotation, by splitting a particle into two pieces inside the ergosphere in such a way that one piece falls into the black hole with negative energy, relative to an observer at infinity, while the other escapes to infinity with more energy than the original particle had. The net result is that the escaping particle carries away some of the black hole's rotational energy, and the black hole spins a little more slowly. Energy has been extracted not from matter surrounding the black hole but from the geometry of spacetime itself. Penrose's discovery was the first demonstration that black holes are not passive structures but can in principle serve as sources of energy, a result that sits at the quiet boundary between physics and the deepest dreams of speculative engineering. Astronomers have developed several techniques for measuring the masses of supermassive black holes in galaxies other than our own, even though those black holes are far too distant for individual stars near them to be resolved by current telescopes. One widely used method relies on the observed relationship between the mass of a supermassive black hole and the velocity dispersion of stars in the central bulge of its host galaxy, a correlation known as the M-sigma relation that was discovered in 2000 and immediately recognized as a clue about the coevolution of black holes and their host galaxies. The M-sigma relation suggests that the mass of a central black hole and the properties of the surrounding galaxy are not independent but are deeply connected, that the growth of black holes and the growth of galaxies are intertwined processes that regulate and limit each other over cosmic time. By measuring how fast the stars in a galaxy's central bulge are moving, a measurement that can be made with spectroscopes at large observatories, astronomers can infer the mass of the invisible black hole at the center with remarkable accuracy, sketching the shape of darkness from the motion of distant stars. The black hole in the center of the M87 galaxy, the same one imaged by the Event Horizon Telescope in 2019, had its mass measured years before that historic image, through the observation of a disk of orbiting gas whose velocity patterns allowed astronomers to calculate the mass of the invisible object at the center using Kepler's laws. The mass of M87* was determined to be approximately 6.5 billion solar masses, making it one of the most massive black holes for which a direct mass measurement has been obtained, and placing its event horizon at a radius of roughly 20 billion kilometers. This measurement was made possible by the Hubble Space Telescope in the 1990s, which could resolve the structure of the gas disk close enough to the center of M87 to detect the velocity gradient that Newtonian and relativistic gravity would predict for a mass of that extraordinary size. When the Event Horizon Telescope image finally arrived in 2019 and the size of the shadow it revealed was compared with the predicted size based on the previously measured mass, the agreement between the two independent measurements was beautifully precise, a quiet triumph for Einstein's theory of gravity across a distance of 55 million light-years. The same equations of general relativity that predict black holes also allow for the theoretical existence of wormholes, structures that connect two separate regions of spacetime through a kind of tunnel, potentially linking distant parts of the universe or even different universes. The simplest theoretical wormhole, known as a Schwarzschild wormhole or Einstein-Rosen bridge, appears mathematically when the full geometry of a black hole solution is extended beyond the event horizon, and it reveals, surprisingly, a second region of spacetime connected to the first through a throat that collapses too quickly for anything to traverse it. More exotic theoretical wormholes, held open by hypothetical forms of negative energy matter, have been studied extensively as thought experiments, and while no physical wormhole has ever been observed or is known to exist, the mathematical relationship between wormholes and black holes has proved to be extraordinarily rich. Recent theoretical work, particularly ideas connecting wormholes with quantum entanglement, has suggested that the geometry of spacetime itself may be woven from quantum connections, a deep and beautiful possibility that remains one of the most active frontiers of theoretical physics. The supermassive black hole at the center of the Messier 87 galaxy, a giant elliptical galaxy located in the Virgo cluster, has a mass of approximately 6.5 billion solar masses, contained within a region of space smaller than our solar system, and it sits at a distance of approximately 55 million light-years from Earth. The Virgo cluster itself is one of the largest nearby galaxy clusters, containing over 1,300 member galaxies, and M87 is its dominant central galaxy, a vast, luminous elliptical system that contains trillions of stars and is home to an extraordinary population of globular clusters, numbering perhaps 15,000. The jet of plasma that M87's central black hole produces, one of the most studied relativistic jets in the sky, extends roughly 5,000 light-years from the galaxy's center and has been observed in radio waves, visible light, and X-rays, offering astronomers a multi-wavelength window into the physics of black hole feeding and energy release. When the Event Horizon Telescope captured its image of this distant, ancient, and profoundly massive object, it was not just a photograph but a geometric proof, visual confirmation that the curved and light-bending spacetime predicted by Einstein does precisely what Einstein's equations say it should do. One of the most surprising discoveries of the past few decades of astrophysics is that the mass of a galaxy's central supermassive black hole is tightly correlated with the properties of the galaxy itself, particularly the mass and velocity dispersion of the stars in the galaxy's central bulge, even though the black hole occupies a region millions of times smaller than the galaxy it inhabits. This correlation suggests that black holes and galaxies do not grow independently of each other, but instead co-evolve through a process of mutual feedback, the black hole growing by consuming gas that falls inward, and the energy it releases heating and dispersing the surrounding gas, regulating the rate at which new stars form. Galaxies that have grown large quickly seem to have large central black holes, and galaxies that formed more slowly or more quietly tend to have proportionally smaller ones, as if the black hole were a quiet governor, moderating the pace of star formation in the galaxy around it. Understanding this intimate relationship between black holes and galaxies has become one of the central organizing questions of modern astrophysics, requiring observations spanning from radio telescopes on Earth to the James Webb Space Telescope looking back at the universe's earliest galaxies. Since its first light observations in 2022, the James Webb Space Telescope has been transforming our understanding of black holes in the early universe, detecting supermassive black holes in galaxies that formed just a few 100 million years after the Big Bang, far earlier and far more massive than most models had predicted. These early black holes pose a genuine puzzle. How did objects with masses of millions or billions of solar masses come to exist when the universe was still in its cosmic infancy, when there had been so little time for stars to form and collapse and for black holes to grow through the usual gradual process of accretion? The discoveries made by Webb have led to renewed interest in models involving the direct collapse of massive gas clouds in the early universe, a process that could seed black holes of tens of thousands of solar masses in a single event, providing a head start for the growth of the supermassive giants observed later. Webb has also detected what appear to be small but luminous active black holes in galaxies that were previously too faint and too distant for older telescopes to characterize, opening an entirely new window into the cosmic history of black hole growth. Long before two black holes merge in the catastrophic final plunge that produces gravitational waves, they may exist for billions of years in a gentle, slowly spiraling binary system, orbiting each other across a distance that gradually decreases as gravitational wave emission carries away energy from the system. These binary black hole systems are believed to form through a variety of pathways, including the evolution of massive binary star systems where both stars eventually collapse, or through the gravitational capture of two black holes in a dense stellar environment like the core of a globular cluster. The inspiral phase, the long, slow approach that may last billions of years, produces gravitational waves that are far too low in frequency and amplitude for current ground-based detectors to sense, but future space-based gravitational wave observatories like the planned LISA, Laser Interferometer Space Antenna, mission will be sensitive to these long, quiet signals. The thought of two massive black holes circling each other in the darkness of a distant galaxy, slowly drawing closer over geological timescales, radiating tiny ripples in the geometry of space-time with each orbit, has a quality of almost meditative patience. One of the most exciting recent developments in gravitational wave astronomy is the growing evidence for a gravitational wave background, a persistent, low-frequency hum of gravitational waves permeating all of space, produced by the combined effect of millions of supermassive black hole binary systems throughout the universe, all slowly spiraling together and radiating into the cosmic fabric. This gravitational wave background was detected not through kilometer-scale laser interferometers but through pulsar timing arrays, networks of very stable, rapidly rotating neutron stars whose pulses arrive at Earth with clockwork regularity, and whose tiny variations in timing carry the imprint of passing gravitational waves. In 2023, for independent pulsar timing array collaborations, in North America, Europe, India, and China, simultaneously announced strong evidence for exactly this kind of gravitational wave background, marking a landmark moment in the emerging field of gravitational wave astronomy. The signal they detected can be thought of as the combined gravitational murmur of countless pairs of supermassive black holes spread across the observable universe, a deep, slow, cosmic drone that has been vibrating through the fabric of space-time for billions of years. Though the mass of Sagittarius A* is approximately 4 million solar masses, a number that sounds enormous by any human scale. The event horizon of our galaxy's central black hole is actually surprisingly compact, with a radius of approximately 12.4 million kilometers. For comparison, the radius of our Sun is about 696,000 kilometers, meaning that the event horizon of the Milky Way's central black hole has a radius only about 18 times that of the Sun, compact enough, in principle, to fit comfortably between the Sun and the orbit of Mercury. The reason Sagittarius A* was so much harder to image than M87* despite being 2,000 times closer is precisely this compactness. Its small angular size and the rapid variability of the gas swirling around it made assembling a coherent image extraordinarily challenging. There is something quietly extraordinary about the fact that an object 26,000 light-years away and millions of times more massive than our Sun has an event horizon that, in absolute terms, would fit within the inner solar system of our familiar celestial home. The cosmic microwave background, the faint, uniform glow of thermal radiation left over from the early universe, when it was about 380,000 years old and the first atoms were forming, provides cosmologists with a map of the early universe, and the subtle patterns in that map contain information about everything that has happened in the cosmos since. Black holes do not appear directly in the cosmic microwave background, but their influence is woven into the map indirectly, through the large-scale structure that supermassive black holes help to shape by regulating galaxy formation, and through the small distortions caused by galaxy clusters that act as gravitational lenses. The Sunyaev-Zeldovich effect, in which cosmic microwave background photons are slightly shifted in energy as they pass through the hot gas in galaxy clusters that themselves formed under the influence of supermassive black hole feedback, leaves characteristic signatures in the background that modern telescopes can detect and analyze. Even in the most ancient light that fills the universe, the patient gravitational work of black holes has left its quiet fingerprints. Just as some massive stars end their lives as black holes, others collapse into neutron stars of extraordinary magnetic intensity, objects known as magnetars, which have magnetic fields roughly a quadrillion times stronger than Earth's, making them the most magnetically intense objects known to exist in the universe. A magnetar's surface magnetic field is so strong that if you were to stand at the distance of the Moon, still only a small fraction of a light-second away, the field would be powerful enough to disrupt the electron clouds of atoms and alter the fundamental chemistry of matter. Magnetars are relevant to the story of black holes because they sit right at the boundary of what a neutron star can be before gravity wins. They represent the most extreme neutron stars, and objects just slightly more massive push past the Tolman-Oppenheimer-Volkoff limit into black hole territory. The existence of magnetars, beautiful, spinning, magnetically intense remnants of stellar death, reminds us that the boundary between a neutron star and a black hole is not sharp or simple but represents a profound and still not fully understood threshold in the physics of matter under extreme compression. The shadow of a black hole, the dark region at the center of the glowing ring seen in images like the Event Horizon Telescope photographs, is not simply a two-dimensional circle but a three-dimensional region of spacetime from which no light reaches our telescopes, and its precise shape is a function of the mass, spin, and the geometry of spacetime described by general relativity. For a non-rotating Schwarzschild black hole, the shadow is predicted to be a perfect circle, while for a rapidly rotating Kerr black hole, the shadow is slightly D-shaped or squashed on one side, a subtle but measurable deviation from perfect circular symmetry that encodes information about the black hole spin. Careful analysis of the Event Horizon Telescope images of both M87* and Sagittarius A** has confirmed that the shadows are consistent with the shapes predicted by general relativity, providing yet another independent test of Einstein's century-old theory in the most extreme gravitational environment accessible to observation. The shape of a shadow cast by an object 55 million light-years away, compared precisely with a mathematical prediction made from century-old equations, and found to agree, this is one of the quieter miracles of modern science. In approximately 4 billion years, the Milky Way galaxy and our nearest large galactic neighbor, the Andromeda Galaxy, Messier 31, are predicted to begin a slow, majestic gravitational dance that will eventually result in their merger, a process that will play out over billions of years and fundamentally reshape both galaxies. During this merger, the supermassive black holes at the centers of both galaxies, Sagittarius A** in the Milky Way and the comparable black hole in Andromeda's core, will eventually spiral toward each other, drawn together by dynamical friction as their surrounding stars interact over hundreds of millions of years. The two supermassive black holes will form a binary system, orbit each other for an extended period, and eventually merge, producing a gravitational wave signal of extraordinary power that would be detectable across vast cosmic distances. The merged galaxy, sometimes nicknamed Milkomeda by astronomers, would not be a spiral like either of its parents but rather a large elliptical galaxy, with a new, larger central black hole that bears the combined mass and spin history of its two quiet predecessors. The gas and dust that spiral inward toward a black hole in an accretion disk do not drift in gently. They orbit at velocities that increase dramatically as they approach the event horizon, following paths dictated by the curvature of spacetime in a way that is an extreme version of how planets orbit the Sun. At the innermost stable circular orbit, the closest orbit at which matter can sustainably circle a black hole before spiraling in, gas moves at a significant fraction of the speed of light, and the exact fraction depends on the spin of the black hole, with gas around a rapidly spinning black hole able to orbit closer and faster than around a non-rotating one. For a maximally spinning black hole, the innermost stable circular orbit comes very close to the event horizon itself, and gas there moves at velocities approaching half the speed of light, speed so fast that the frictional heating of the gas raises its temperature to millions of degrees. This extreme heating transforms the accretion disk from a passive disk of orbiting gas into one of the most brilliant radiating structures in the universe, converting gravitational potential energy into light with an efficiency that outperforms any nuclear process by a factor of many times. Before the physics of black holes was understood, the idea of a darkness so complete that light itself could not escape it appeared independently in various philosophical and literary traditions. There is something in human intuition that reaches toward the concept of an ultimate boundary, a place from which no message can return. When the concept of black holes entered popular culture through science fiction in the mid-20th century, they were often imagined as dangerous, devouring voids, but the more nuanced reality that science revealed was, in many ways, stranger and more beautiful than any fictional conception. Films like Interstellar, 2014, worked with physicist Kip Thorne to produce some of the most scientifically accurate visual representations of black holes ever rendered, and the spinning black hole Gargantua depicted in the film was based on a full general relativistic rendering that even taught Thorne something new about the appearance of accretion disks. The relationship between human culture and the concept of black holes has been one of gradual, deepening wonder, from a philosophical thought experiment to a mathematical prediction to a detected gravitational signal to an actual photograph. a journey of understanding that mirrors the universe's own patient, unfolding revelation. To a distant observer watching an object fall toward a black hole's event horizon, something profoundly counterintuitive happens due to gravitational time dilation. The infalling object appears to slow down and redden as it approaches the horizon, its light stretching to longer and longer wavelengths, its apparent motion freezing asymptotically, never quite seeming to cross the horizon, while fading gradually into invisibility. From the perspective of the infalling object itself, however, no such slowdown is experienced. The horizon is crossed smoothly, without any special sensation at that precise moment, in a finite proper time that depends on the mass of the black hole. These two completely different descriptions of the same event, the distant observer's perspective and the infalling observer's perspective, are both entirely valid and correct, and the apparent paradox of how something can never cross the horizon and yet cross it without incident is one of the most subtle and beautiful features of general relativity. The resolution lies in understanding that in relativity, there is no universal clock, no single correct perspective, only the observer's own proper time, and the geometry of space-time that connects different observers' experiences in a precise and self-consistent way. Among the fascinating corners of modern astrophysics is the study of exotic compact objects, theoretical structures that might mimic some of the external properties of black holes without actually possessing an event horizon, offering a possible window into new physics beyond general relativity. Objects such as gravastars, boson stars, and various quantum gravity-inspired compact objects have been proposed as theoretical alternatives to black holes, and determining whether any such objects could explain the observations we attribute to black holes is an active area of research. The Event Horizon Telescope images, along with gravitational wave observations, have placed strong constraints on many of these alternatives. The data is very consistent with the predictions of standard black holes as described by general relativity, making the case for true black holes compelling. Nevertheless, the search for subtle deviations from the predictions of standard black hole physics remains one of the most fascinating pursuits in observational astrophysics, a quiet search for the unexpected in the most thoroughly studied darkness in the cosmos. Magnetic fields play an extraordinarily important role in the physics of accretion disks and jets around black holes, threading through the disk material and interacting with the plasma in ways that help transport angular momentum outward, allowing material to spiral inward, and that help to launch and collimate the relativistic jets that some active black holes produce. The Event Horizon Telescope collaboration has been developing the capability to measure the polarization of light from the M87* accretion disk, a technique that reveals the direction and structure of magnetic fields near the event horizon, and in 2021 released polarization maps showing ordered magnetic field structures in the inner accretion disk. These polarization maps showed that the magnetic field near M87* has a relatively ordered, spiral structure, consistent with models in which the field plays a key role in the energy transport processes of the accretion disk and the launching of the famous M87 jet. Understanding the detailed magnetic field structure of black hole accretion systems is one of the key frontiers of modern high-resolution radio astronomy, and future next-generation Event Horizon Telescope observations will extend this capability to even finer angular scales. In 2012, a group of physicists including Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully published a paper proposing what became known as the firewall paradox, a thought experiment suggesting that if quantum information is truly preserved as it escapes from a black hole, then the region just inside the event horizon might not be the smooth, empty spacetime that general relativity predicts, but instead a violent, hot firewall of high-energy radiation. The firewall idea set off an intense and productive debate in the theoretical physics community because it places three of physics' most cherished principles in direct conflict: the equivalence principle of general relativity, the unitarity of quantum mechanics, and the principle that information escapes from evaporating black holes. At least one of these principles, the argument suggests, must be modified or abandoned, but which one, and how, remains deeply contested and represents one of the most exciting ongoing debates in fundamental physics. The firewall paradox is, in a sense, one of the most honest and beautiful things that theoretical physics can produce. A clear, sharp demonstration that our current best theories are incomplete, and a precise guide pointing toward where the next deeper theory must improve on its predecessors. One of the surprising gifts that black hole physics has given to mathematics is the discovery of deep connections between the geometry of curved spacetime and the algebra of quantum mechanics, connections that have led to new mathematical insights in both physics and pure mathematics. The study of black hole thermodynamics, treating black holes as thermodynamic systems with temperature, entropy, and the ability to exchange energy with their surroundings, has produced the 4 laws of black hole mechanics, which are formal analogues of the 4 laws of ordinary thermodynamics applied to black holes. These 4 laws, derived from general relativity by Stephen Hawking, James Bardeen, and Brandon Carter in 1973, describe how the mass, area, surface gravity, and angular momentum of a black hole change in response to perturbations, and their formal resemblance to the laws of thermodynamics was initially thought to be a curious coincidence until Hawking's discovery of black hole radiation confirmed it was deeply real. The beauty of these 4 laws is that they transformed black holes from objects of astronomical interest into thermodynamic systems, extending the reach of thermodynamics, one of the oldest and most beautiful frameworks in physics, to the most extreme objects in the cosmos. An accretion disk surrounding a black hole is one of the most physically complex and beautiful structures in the universe. A flattened, rotating disk of gas and dust that extends from the innermost stable circular orbit outward to distances that can be hundreds or thousands of times the radius of the event horizon. Moving outward from the center, the disk goes from its hottest, most luminous inner regions, where gas can reach temperatures of millions of degrees and emits X-rays, through progressively cooler middle regions that emit extreme ultraviolet and ultraviolet light, to its cooler outer zones that glow in visible and infrared light. The physics of how material moves through the disk, slowly losing angular momentum and spiraling inward, is governed by a form of turbulence driven by a beautiful magnetic instability called the magnetorotational instability, which was properly understood only in the early 1990s and represented a breakthrough in our understanding of how accretion disks actually work. The result of all this complex physics is a glowing, layered, magnetically active disk that is simultaneously one of the most efficient energy machines in the universe and one of the most visually spectacular, its concentric rings of decreasing temperature creating a natural gradient from brilliant blue-white at the center to warm red at the margins. When 2 black holes merge and form a single larger black hole, the newly formed object does not immediately settle into its final equilibrium state. Instead, it vibrates and oscillates for a brief time, radiating gravitational waves in a characteristic pattern known as quasi-normal modes, analogous to the way a struck bell rings at specific frequencies determined by its shape and material. These quasi-normal oscillations carry a precise fingerprint of the final black hole's mass and spin, encoded in the frequency and damping time of the gravitational wave signal, and measuring them provides a direct, independent determination of the properties of the merged object. The gravitational wave signals detected by LIGO and Virgo all contain this ring-down phase after the merger, and analyzing it has confirmed that the merging objects are consistent with black holes and that the final merged state matches the predictions of general relativity for a Kerr black hole. The image of a newly formed black hole ringing like a cosmic bell, its gravitational vibrations propagating outward across a billion light-years of space, is one of the most vivid and beautiful pictures that theoretical astrophysics has ever produced. The distance from Earth to Sagittarius A*, the supermassive black hole at the center of the Milky Way, is approximately 26,000 light-years, meaning that the light we use to observe the galactic center today left that region of space approximately 26,000 years ago, when anatomically modern humans were still in the Stone Age, painting magnificent figures on cave walls in Europe and Asia. This distance means that any changes happening at the galactic center right now, any flare of activity from Sagittarius A*, any cloud of gas falling toward the event horizon, will not be known to Earth for another 26,000 years, if they are ever detectable at all. The intervening 26,000 light-years of space between Earth and the galactic center is not empty but filled with dense clouds of gas and dust that absorb almost all visible and ultraviolet light from the galactic center, which is why our own galaxy's black hole remained unconfirmed for so long. It can only be seen in radio waves, infrared light, and X-rays, which penetrate the dust more easily. There is a quiet and humbling beauty in the thought that our closest supermassive black hole, the anchor of our own galaxy, is separated from us by a gulf of space so wide that the history of all human civilization would fit many times over in the time it takes light to cross it. String theory, the framework of theoretical physics that proposes that the fundamental constituents of nature are not point particles but tiny, vibrating one-dimensional objects called strings, has a deep and productive relationship with the physics of black holes, using them as test cases for the theory's predictions and consistency. One of the early successes of string theory was the calculation by Andrew Strominger and Kamran Vafa in 1996 of the exact entropy of a specific type of extremal black hole. A black hole at the boundary between the regime where it has an event horizon and where it would not, and the agreement between their calculation and Bekenstein's formula was striking. String theory also provides one of the main frameworks for thinking about the information paradox, through the ADS-CFT correspondence, which relates a gravitational theory in certain curved spacetimes to a quantum field theory on the boundary of that spacetime without gravity, offering a perspective in which information is manifestly preserved. The relationship between string theory and black holes is not simply one of application. Black holes have helped to shape and constrain the development of string theory itself, serving as thought experiments that any fundamental theory of quantum gravity must successfully account for. The very first black holes in the universe are believed to have formed within the first few 100 million years after the Big Bang, born from the deaths of the first generation of stars, known as population 3 stars, which were almost entirely made of hydrogen and helium and are thought to have been extraordinarily massive, perhaps hundreds or even thousands of times more massive than our Sun. These first stars burned bright and brief, exhausting their fuel quickly and collapsing into black holes whose masses could have been in the hundreds to thousands of solar masses, a scale never seen in the current universe's star formation, where heavier elements from previous stellar generations changed the process. The black holes left behind by population 3 stars may have been the seeds around which the first galaxies assembled, their gravity concentrating gas and triggering new star formation in a process that built up, over billions of years, the rich and diverse cosmic structures we observe today. Looking back in time with instruments like the James Webb Space Telescope, astronomers are now beginning to glimpse this earliest epoch of black hole formation. Seeing the universe at an age of just a few 100 million years and finding evidence of black holes that are already surprisingly massive, raising new questions about how quickly those first seeds grew. The story of humanity's first confirmed black hole begins in 1964, when a rocket-borne X-ray detector launched above the atmosphere discovered a brilliant X-ray source in the constellation Cygnus. A source so powerful and so compact that it quickly attracted the attention of astronomers worldwide. Named Cygnus X1, this X-ray source was found to be associated with a massive blue supergiant star, and careful measurements of the star's orbital motion revealed that it was being pulled by an invisible companion with a mass far exceeding what any neutron star could be. The debate over whether Cygnus X1's invisible companion was truly a black hole was the subject of a famous gentleman's wager between Stephen Hawking and Kip Thorne. Made in 1974, Hawking bet against it being a black hole as an insurance policy for his theoretical work, while Thorne bet in favor. By 1990, the evidence had become overwhelming, and Hawking graciously conceded the bet, paying Thorne with a subscription to a magazine, a quiet and good-natured acknowledgement that the universe had confirmed one of the most consequential predictions of modern physics. Though Stephen Hawking made important contributions to cosmology throughout his career, many physicists consider the theoretical discovery of Hawking radiation to be his single most important and enduring scientific achievement, a result so unexpected that it took several years to be widely accepted, and whose implications continue to reverberate through theoretical physics today. Hawking arrived at his discovery through a remarkable synthesis of three fields that had rarely been brought together before: general relativity, which described the curved space-time geometry of the black hole; quantum field theory, which described the behavior of particles and fields in that curved space-time; and thermodynamics, which provided the conceptual framework for understanding what the resulting particle emission meant. The calculation was deeply counterintuitive. It showed that something classified by general relativity as black was, from the perspective of quantum mechanics, actually emitting a faint thermal glow, and it revealed for the first time a fundamental tension between the two pillars of modern physics that has not yet been resolved. Hawking himself has said that if he could have one wish granted after his death, it would be to see Hawking radiation detected, a wish that may one day be fulfilled, perhaps by observing small primordial black holes or by constructing laboratory analogues of black holes in exotic quantum systems. Globular clusters, compact, roughly spherical collections of hundreds of thousands to millions of stars, bound tightly together by gravity and orbiting outside the main disk of our galaxy, have long been suspected to harbor intermediate-mass black holes at their centers, formed perhaps by the repeated merging of smaller black holes or very massive stars in the dense core. The evidence for intermediate-mass black holes in globular clusters has been tantalizing but elusive for decades. Studies of the velocities of stars near the centers of clusters like Omega Centauri, 47 Tucani, and NGC 6388 have sometimes suggested the presence of a central unseen mass, but interpreting the data cleanly has proved difficult. More recent work with gravitational wave observations has detected mergers involving black holes that could be consistent with intermediate-mass black holes, and the growing catalog of gravitational wave events is providing new statistical information about the mass distribution of merging black holes. The beautiful, ancient, gem-like globular clusters scattered throughout the halo of the Milky Way, some of them nearly as old as the universe itself, may be quietly harboring some of the most interesting and scientifically valuable black holes accessible to study. Not all active galactic nuclei are brilliant quasars blazing with the light of 1 trillion suns. Many supermassive black holes, including our own Sagittarius A*, spend much of their time in a quiescent or low luminosity state, consuming very little material and producing only modest emission compared to the most active examples. These low-luminosity active galactic nuclei are believed to be accreting material through a different physical process than the geometrically thin, optically thick disk of an actively feeding quasar. Instead, their accretion is thought to proceed through a geometrically thick, radiatively inefficient flow, sometimes called an advection-dominated accretion flow. In this low-luminosity state, the black hole still influences its environment, producing weak jets and heating surrounding gas, but does so with a quiet subtlety that makes it far more difficult to detect and study than its more dramatic, quasar phase counterparts. Sagittarius A* occasionally brightens briefly in X-ray and infrared emission, events called flares that may be associated with small amounts of material falling suddenly closer to the event horizon. But these flares are transient and modest, a quiet punctuation in an otherwise deeply peaceful existence. Among the most energetic events in the observable universe are gamma-ray bursts, brief, intense flashes of gamma-ray radiation that can last anywhere from a fraction of a second to several minutes and that briefly outshine the entire observable universe in gamma-ray light. And many of the most energetic long-duration gamma-ray bursts are believed to signal the birth of a new black hole. When the core of a very massive rotating star collapses directly to a black hole, the infalling material can form a thick accretion torus around the newly formed black hole, and the interaction between this torus and the black hole's magnetic field and spin drives an extraordinarily powerful jet of energy that punches through the collapsing star and emerges to produce the gamma-ray burst we observe. The afterglow of a gamma-ray burst, the softer, longer-lasting emission in X-rays, visible light, and radio waves that follows the initial flash, has been used to study the environments of these remarkable events and to confirm that many of them occur in star-forming regions of distant galaxies. The fact that the birth cry of a new black hole can be seen across billions of light-years of space means that gamma-ray bursts serve as extraordinary cosmic beacons, allowing astronomers to study some of the most distant and ancient events in the universe's history. Perhaps the most important role that black holes play in contemporary theoretical physics is as laboratories, thought experiments and mathematical test cases for the development of a theory of quantum gravity, the long-sought unification of general relativity and quantum mechanics. Every major candidate theory of quantum gravity, string theory, loop quantum gravity, causal dynamical triangulations, asymptotic safety, and others, must confront and account for the physics of black holes, particularly the information paradox, the nature of the singularity, and the statistical origin of black hole entropy. The fact that black holes occupy the extreme regime where both gravity and quantum mechanics are equally important, where the energy scales of both theories overlap, makes them uniquely valuable as conceptual proving grounds for any theory that aspires to describe all of nature. In a deep sense, solving the full mystery of black holes and resolving all the paradoxes they generate may be inseparable from achieving one of science's oldest and deepest ambitions: a single, unified, beautiful theory of all the fundamental forces and particles of nature. The Laser Interferometer Gravitational Wave Observatory, LIGO, which made the first direct detection of gravitational waves in 2015, is one of the most precise scientific instruments ever constructed, designed to measure length changes smaller than 1,000th the diameter of a proton across arms 4 kilometers long. LIGO works by splitting a laser beam into two beams sent down its two perpendicular arms, reflecting them off mirrors, and recombining them to produce an interference pattern. When a gravitational wave passes, it stretches one arm and compresses the other, changing the interference pattern in a characteristic way that can be recorded and analyzed. The mirrors that reflect the laser beams in LIGO's arms are among the quietest objects in the world, isolated from Earth's vibrations through multiple layers of sophisticated suspension systems, cooled to reduce thermal noise, and polished to such precision that their reflective surfaces deviate from perfect flatness by less than the size of an atom. When the first gravitational wave signal arrived in September 2015, it was so consistent with the predictions for a black hole merger that the team's immediate reaction was one of awed disbelief. A quiet, sustained moment of recognizing that something genuinely new and ancient had just been heard for the first time. The phenomenon of frame dragging, where a rotating mass drags the surrounding spacetime into rotation with it, was theoretically predicted by Austrian physicists Joseph Lenz and Hans Thirring in 1918, just 3 years after general relativity was published, and it was given their names in what became known as the Lenz-Thirring effect. For a rotating black hole, frame dragging reaches its maximum theoretical intensity at the event horizon, where the dragging is so strong that spacetime itself is dragged into rotation at the same angular velocity as the hole, a condition called the horizon rotates with the hole. The Gravity Probe B satellite, launched by NASA in 2004, measured the Lenz-Thirring effect around the much more modest rotation of the Earth itself, confirming the predicted frame dragging of Earth's rotation on the surrounding spacetime to within about 19% of the theoretical value. Around rapidly spinning black holes, frame dragging is millions of times stronger than around Earth, and it plays a fundamental role in the dynamics of accretion disks, the launching of jets, and the evolution of the orbits of any objects moving in the vicinity of the black hole. The brightest quasar ever discovered, J05294351, announced in 2024, is powered by a black hole that is consuming matter at the rate of approximately 1 solar mass per day, producing a luminosity roughly 500 trillion times that of our Sun and making it the most luminous object yet known in the observable universe. The black hole at the heart of J05294351 has a mass estimated at roughly 17 to 19 billion solar masses, making it one of the most massive black holes known, and its extraordinary brightness is a direct consequence of the extraordinary amount of gravitational potential energy being converted to radiation as infalling matter spirals through the accretion disk. Despite its breathtaking luminosity, J05294351 is located at such an extreme distance, roughly 12 billion light-years from Earth, that it appears as nothing more than a point of light in the sky, its true nature revealed only through spectroscopic analysis that shows the characteristic spectral signatures of an actively feeding quasar. This object, the brightest known thing in the universe, has been sitting in the night sky all along, catalogued in astronomical surveys but mistaken for a star, its true identity only revealed through careful spectroscopic work in 2023. Occasionally, a star wandering through the galaxy follows an orbit that brings it too close to a supermassive black hole, close enough that the tidal forces generated by the black hole's gravity exceed the internal gravitational forces that hold the star together, and the star is torn apart in an event known as a tidal disruption event. The stellar material, after the star is disrupted, does not all fall immediately into the black hole. Instead, roughly half falls inward and forms a temporary accretion disk, while the other half is flung outward on hyperbolic orbits, producing a dramatic but transient brightening of the galactic nucleus that can outshine the entire host galaxy for weeks or months. Astronomers have now observed dozens of tidal disruption events across the universe, identified as brief, distinctive flares of optical, ultraviolet, and X-ray emission from otherwise quiet galaxy centers. And these events are providing a new way to study the physics of accretion and the properties of the supermassive black holes that cause them. The thought of a star, a ball of nuclear fire perhaps billions of years old, being slowly and gracefully unspooled by the gravity of a black hole into a long, luminous ribbon of gas is, in the language of astrophysics, one of the most visually poetic events in the universe. The Event Horizon Telescope is not a single instrument but a collaboration of radio telescope facilities distributed across the globe, which are synchronized and combined using a technique called very long baseline interferometry to effectively simulate a telescope the size of Earth. The data collected by each of these facilities during an observation campaign is recorded on high-capacity hard drives that are then physically shipped to correlation centers in the United States and Germany, where the signals are precisely aligned using atomic clock timestamps and combined to produce the final image. The beauty of this approach is that it turns the entire surface of the Earth into a collaborative scientific instrument, a planet-sized telescope that is itself a testament to what becomes possible when human knowledge, curiosity, and effort are gathered and focused with sufficient precision. The four laws of black hole mechanics, derived in the early 1970s, bear a deep structural resemblance to the four laws of classical thermodynamics, a resemblance so precise that it was eventually understood not as a coincidence but as a profound truth about the relationship between gravity, quantum mechanics, and statistical physics. The zeroth law states that the surface gravity of a black hole is constant over its event horizon, analogous to the zeroth law of thermodynamics, which states that temperature is uniform throughout a system in thermal equilibrium. The first law relates changes in a black hole's mass, area, and angular momentum in a way analogous to the first law of thermodynamics relating changes in energy, entropy, and volume, and with the identifications temperature equals surface gravity and entropy equals horizon area, the two laws become formally identical. The second law, that the total area of event horizons in any process can only increase, is the black hole analog of the thermodynamics second law stating that entropy can only increase, and Hawking's area theorem proving it from general relativity was one of the key results that made physicists take the thermodynamic analogy seriously before Hawking radiation provided the final confirmation. The next generation of gravitational wave detectors, currently in planning and early development phases, will be vastly more sensitive than the current LIGO, Virgo, and Kagra observatories, opening new windows on the black hole population of the universe and enabling entirely new science. Ground-based third-generation detectors like the Einstein telescope, proposed for Europe, and Cosmic Explorer, proposed for the United States, would have arm lengths of 10 to 40 kilometers and sensitivities perhaps 10 to 100 times better than current detectors, allowing them to detect black hole mergers throughout the entire observable universe. The space-based LISA, Laser Interferometer Space Antenna, mission, planned for launch in the mid-2030s, will consist of 3 spacecraft separated by 2.5 million kilometers, connected by laser beams, and will be sensitive to gravitational waves from supermassive black hole mergers and other low-frequency sources invisible to ground-based detectors. Together, these future instruments will transform gravitational wave astronomy from a few dozen detections to potentially millions, creating a comprehensive census of the black hole population across cosmic time and potentially revealing entirely unexpected sources of gravitational wave emission. In 2019 and 2020, a series of papers by several groups of physicists, building on ideas from quantum gravity, the ADS-CFT correspondence, and detailed calculations of quantum fields near black holes, reported a major step forward in understanding how information might be preserved in the process of black hole evaporation. These papers used a technique called the island formula or replica wormholes to calculate the entropy of Hawking radiation and showed that, when certain quantum gravitational effects are taken into account, the entropy of the radiation follows the Page curve, rising and then falling as the black hole evaporates, consistent with information being preserved. The physical picture that emerged suggested that, at late times in a black hole's evaporation, quantum gravitational effects create contributions to the path integral that correspond to replica wormholes, subtle geometric connections in spacetime that allow information to leak into the outgoing radiation. While these results represent significant mathematical progress and have been hailed as a major advance, many physicists caution that the full physical mechanism remains unclear, and the information paradox, while wounded, is not yet completely resolved. It remains one of the most productive open questions in fundamental physics. One of the most important conceptual points about black holes, one that often surprises people when they first encounter it, is that a black hole does not have a physical surface of any kind. The event horizon is not a solid boundary, a wall, or even a place where any unusual quantity of matter is concentrated. The material that originally collapsed to form the black hole has all fallen toward the singularity at the center, and the event horizon is nothing but a geometric location in space-time, the boundary of the region from which no causal curve can escape to infinity, as intangible and insubstantial as any imaginary line drawn in empty space. If you were to fall through the event horizon of a sufficiently large black hole, you would not feel any physical impact or encounter any surface. The space you passed through would feel, at that moment, like perfectly ordinary empty space, with no obvious marker that you had just crossed the most consequential boundary in the universe. This is part of what makes the event horizon so philosophically interesting. It is a boundary defined entirely by global properties of the space-time, not by any local physical feature, a line drawn not in matter but in the structure of time and space itself. Some of the most scientifically interesting black hole systems are those in which a black hole orbits not an ordinary star but a neutron star, the other major type of compact stellar remnant, forming what is called a black hole neutron star binary. These systems are expected to exist throughout the Milky Way and other galaxies, formed when two massive stars in a binary system both complete their stellar evolution and undergo core collapse, with the more massive one forming a black hole first and the less massive one later forming a neutron star. The Gravitational Wave Observatory LIGO detected its first black hole neutron star mergers in 2021, with two such events detected within days of each other in January of that year, GW200105 and GW200115, providing the first direct observational confirmation of this type of system. These mergers are of particular scientific interest because they may produce electromagnetic counterparts, flashes of light and other radiation, when the neutron star is disrupted by the black hole's tidal forces, similar to the neutron star merger that was famously observed in 2017 alongside its gravitational wave signal. Gravitational wave astronomy has become a global scientific enterprise, with observatories now operating or under development on multiple continents, each contributing to an increasingly sensitive worldwide network that can not only detect gravitational waves but also precisely localize their sources on the sky. The two LIGO detectors, at Hanford, Washington, and Livingston, Louisiana, form the core of the network, separated by about 3,000 kilometers so that the time difference in their detection of a gravitational wave signal can help determine the direction from which the waves arrived. The Virgo detector in Cassina, Italy, added to the network in 2017, and the Kagra detector in the Kamioka mine in Japan, which began observing in 2020, have extended the network's sky coverage and sensitivity, and future editions of a detector in India, LIGO India, will further improve the network's ability to localize sources. The geographic distribution of these observatories, from the Washington Desert to the Louisiana Bayou to the Italian countryside to the Japanese mountains, represents a quiet, collaborative global commitment to listening to the universe through the most delicate and precise sense humanity has yet developed. The size of a black hole's shadow, the dark region at the center of the glowing ring seen in Event Horizon Telescope images, is directly proportional to the mass of the black hole and inversely proportional to the distance to the black hole, with the proportionality constant determined by general relativity and the speed of light. For M87*, the shadow has an angular diameter of approximately 42 microarcseconds as seen from Earth, a vanishingly small angle equivalent to the apparent size of a golf ball on the surface of the Moon as seen from Earth. Resolving an angular scale this small requires a telescope with an angular resolution comparable to 42 microarcseconds, which, at the radio wavelengths used by the Event Horizon Telescope, 1.3 millimeters, demands an effective telescope aperture equal to the diameter of the Earth. This is why the Event Horizon Telescope needed a global network of observatories, not because any individual telescope was insufficient in sensitivity, but because the angular resolution required to see the shadow of a black hole could only be achieved by combining signals from instruments separated by intercontinental distances. The universe is not only home to black holes, it is itself expanding, and this expansion has profound implications for the long-term future of black holes in the cosmos and for how we think about the relationship between black hole physics and cosmology. In the very far future, the accelerating expansion of the universe, driven by the mysterious dark energy that comprises roughly 68% of the total energy content of the cosmos, will eventually cause all galaxies outside our local group to recede from us faster than light can bridge the gap, making the rest of the universe causally disconnected from our own corner of space. In this cosmological scenario, the surviving black holes of the local group, including the merged remnant of Sagittarius A** and the Andromeda black hole, will sit in an increasingly isolated island of matter, slowly evaporating through Hawking radiation over timescales of 10 to the power of 100 years. The image of the very last black holes glowing with their final whispers of Hawking radiation in an otherwise dark, cold, and empty universe is one of the most serene and meditative conclusions that physics has ever traced for the long-term narrative of the cosmos. One of the most elegant results in the thermodynamics of black holes is the Bekenstein-Hawking formula for the entropy of a black hole, which states that the entropy is equal to 1/4 of the event horizon's area measured in Planck units, a formula that is arguably one of the most beautiful and profound equations in all of theoretical physics. Written out, the entropy S equals the area A divided by 4 times the Planck length squared, connecting the macroscopic geometry of the event horizon, a quantity from general relativity, to a measure of microscopic disorder, a quantity from statistical mechanics, through the Planck length, a quantity from quantum gravity. The Planck length, approximately 1.6 times 10 cubed meters, is the scale at which quantum gravitational effects become important, and the appearance of the Planck area in the entropy formula is a hint that the microscopic degrees of freedom responsible for black hole entropy are quantum gravitational in nature. The Bekenstein-Hawking formula sits at the intersection of the three great pillars of modern physics: general relativity, quantum mechanics, and statistical mechanics, and any theory of quantum gravity must reproduce it as a fundamental result, making it a precious benchmark for the theories humanity has yet to fully construct. One of the most beautiful and productive analogies in modern physics is the correspondence between black holes in spacetime and so-called sonic holes or dumb holes in ordinary fluids, a connection first pointed out by physicist William Unruh in 1981. In a sonic hole, a fluid flows so fast in some region that sound waves cannot propagate upstream. They are carried along by the flow and cannot escape from the region of supersonic flow, in exact analogy with how light cannot escape from a black hole. This analogy is not merely superficial. The mathematics describing Hawking radiation from a black hole can be applied to predict a thermal radiation of sound waves from a sonic hole, and this sonic Hawking radiation has actually been observed in laboratory experiments using ultra-cold atomic systems called Bose-Einstein condensates. The laboratory observation of sonic Hawking radiation in 2019 by Jeff Steinhauer's group at the Technion in Israel was a landmark achievement, not because it directly confirmed Hawking radiation from astronomical black holes, but because it confirmed the underlying quantum physical mechanism that Hawking's calculation relies on, in a controllable, observable laboratory setting. The Milky Way galaxy contains an estimated 10 million to 1 billion stellar mass black holes, but the vast majority of them are isolated, surrounded by no material to accrete, and therefore completely invisible to current telescopes, detectable only if they happen to pass in front of a background star and reveal themselves through gravitational microlensing. The black holes that have been measured and confirmed in the Milky Way are primarily those in X-ray binary systems, where they are actively consuming material from a companion star and glowing in X-rays, and the current catalogue of confirmed stellar black holes in the Milky Way numbers in the dozens. Among the most massive known stellar black holes in the galaxy is Cygnus X1, with about 21 solar masses, and the recently discovered Gaia BH1 and Gaia BH2, isolated black holes detected through the gravitational wobble they induce in companion stars using the precise astrometry of the Gaia satellite. The detection of isolated, non-accreting black holes through astrometric wobble and microlensing is one of the most exciting frontiers of modern stellar astronomy, and the Gaia mission and future surveys are expected to reveal many more of these quiet, dark wanderers hidden throughout our galaxy. The highest energy cosmic rays, subatomic particles that arrive at Earth from space with energies far exceeding anything achievable in human-built particle accelerators, are believed to originate from the environments of active black holes, where particles can be accelerated to extraordinary energies through processes connected to the jets and magnetic fields around accreting supermassive black holes. The process of particle acceleration in the vicinity of black holes is not yet fully understood, but leading models involve a combination of the strong electric fields generated by the rotating magnetosphere of the black hole, multiple shock acceleration events in the relativistic jet, and the enormous reservoir of energy available in the spin of the black hole itself. Ultra-high energy cosmic rays, those with energies above 10 to the power of 1 electron volts, lose energy relatively quickly as they travel through the universe through interactions with the cosmic microwave background radiation, meaning that the sources of the most energetic cosmic rays must be relatively nearby on cosmological scales. The Pierre Auger Observatory in Argentina, one of the world's largest cosmic ray detectors, covering an area of 3,000 square kilometers, is dedicated to studying these highest energy particles and finding correlations between their arrival directions and the positions of active black holes in the nearby universe. When a black hole's accretion rate becomes sufficiently high, the radiation pressure from the outgoing photons pushes back against the infalling gas hard enough to potentially halt further accretion. And the luminosity at which this balance is achieved is called the Eddington luminosity, named for the British astronomer Arthur Stanley Eddington, who derived it in 1916. The Eddington luminosity depends on the mass of the black hole. More massive black holes can sustain higher luminosities before radiation pressure halts accretion, and it sets a natural scale for the maximum sustainable luminosity of a black hole accreting through a thin disk. Quasars and other active black holes are often found to be accreting at rates close to or somewhat below the Eddington limit, and some objects appear to exceed it briefly in what are called super-Eddington accretion events, where the disk geometry changes and the effective radiation pressure is reduced. The existence of the Eddington limit is one reason why the growth of supermassive black holes in the early universe is so puzzling. Sustained growth at or below the Eddington rate may not be sufficient to build billion solar mass black holes within the first billion years of cosmic time, suggesting that super-Eddington accretion or direct collapse scenarios may have been necessary. The system of naming black holes in the universe follows conventions borrowed from the broader traditions of astronomy, with different types of black holes inheriting the names or catalog identifiers of their host systems, their X-ray source catalogs, or the gravitational wave event catalogs that identified them. X-ray binary black holes are typically named for the constellation in which they appear and a number indicating their relative brightness, hence Cygnus X1, first X-ray source in the Swan constellation, and V404 Cygni, the 404th variable star catalogued in Cygnus. Gravitational wave events are named by the date of detection and observation run. GW 150914 was the gravitational wave detected on September 14, 2015. GW 170817 was the famous neutron star merger of August 17, 2017, giving each event a unique and informative identifier that encodes both the nature of the detection and the moment of discovery. The supermassive black holes imaged by the Event Horizon Telescope M87*, the asterisk denoting the compact central object in Messier 87, and SGR A*, Sagittarius A*, follow a different convention, inheriting modified forms of the names of their host objects, and these simple, understated labels carry the weight of some of the most consequential observations in the history of science. The observable universe, the region of space from which light has had time to reach us since the Big Bang, approximately 93 billion light-years across in diameter, contains an estimated 2 trillion galaxies, and each of those galaxies is thought to harbor at least one supermassive black hole at its center. 2 trillion supermassive black holes, each containing millions to billions of solar masses, distributed across the observable universe, and in addition, perhaps 40 quintillion stellar mass black holes distributed among the stars of those 2 trillion galaxies, represents a cosmic inventory of black holes that staggers any attempt at intuitive comprehension. And yet, even with all these black holes, the fraction of the universe's total mass that they represent is relatively modest. Estimates suggest that stellar mass black holes account for perhaps a few % of the total mass in stars, and supermassive black holes, despite their enormous individual masses, are small compared to the total mass of their host galaxies. The universe is, in a quiet and beautiful sense, permeated by black holes, not as rare exceptions or dramatic catastrophes, but as common, patient, and fundamental features of the cosmic landscape, as natural a part of the universe as stars and galaxies and the vast expanses of dark space between them. Even galaxies that currently host quiet, dormant supermassive black holes may have been far more active in their past. The history of the universe tells a story in which black hole activity was far more intense billions of years ago, when galaxies were younger and richer in the gas that feeds active galactic nuclei. The peak of quasar activity in the universe occurred roughly 10 to 12 billion years ago, a cosmic epoch known as cosmic noon, when black holes across the universe were consuming gas at prodigious rates and producing luminosities that sculpted the large-scale structure of the intergalactic medium. Since that peak, the universe has gradually exhausted much of the easily available gas supply, and most black holes have settled into long, quiet periods of dormancy, like banked fires that burn very low but are never completely extinguished. A dormant supermassive black hole can be reawakened by a supply of new gas, provided by a galaxy merger, a tidal disruption event, or the slow infall of cooling gas from the galaxy's halo. And so every large galaxy in the universe carries at its center a sleeping potential that may, given the right circumstances, one day blaze again as a quasar. And so, dear listener, we arrive together at the gentle end of our journey through the quietest and most magnificent structures the universe has ever fashioned, black holes, those patient anchors of galaxies, those dark keepers of the cosmos's deepest mathematical secrets. You have traveled tonight through 13.8 billion years of cosmic history, from the first moments of the universe's quiet beginning to the far future when the last black holes will glow their final, faint hawking warmth into an otherwise still and peaceful darkness. Wherever you are right now, in whatever room, in whatever light or darkness, the universe is curled softly around you, its galaxies slowly turning, its black holes resting at their centers like the still eyes of endless cosmic spirals, patient and enduring and deeply, beautifully present. Let your breath slow, let your body sink, and let the quietness of the cosmos, so much larger and older and more wonderful than any worry or urgency, carry you gently into rest.